the last class we saw how the carbon chemical shifts in one dimensional carbon NMR can be calculated, predicted based on the structures. We looked at a few examples, given some rules, and these are all empirical rules, and how we calculate. Similarly, we had seen this also for protons a few classes ago. So, if you now look at this slide, what this slide is depicting is a very interesting thing, and the thing is that in chemical shifts, if you see on the x axis is carbon chemical shifts and on the y axis is hydrogen proton chemical shifts. So, for a given CH carbon hydrogen pair is plotted here. So, for example, if a proton has a chemical shift close to 0, this carbon is around -10. Similarly, if some particular, this is again from a large number of molecules, large number of CH chemical shifts, this has been taken. This is a plot again from one of the research articles. What it says is that whenever you have a carbon proton pair, so we are basically looking at this kind of a system. So, we are looking at a CH pair. So, this is H is on the x axis, y axis, what is plotted, and for the same hydrogen carbon this is plotted on the x axis. Okay. So, this is for a particular pair. So, we take a large number of such pairs from a large number of molecules and is plot is shown here. So, what it says is that if the for a given CH moiety like this, if the hydrogen chemical shift goes upfield means towards upper side, the carbon chemical shift is also upfield towards the 0 side. Similarly, if carbon chemical shift goes down, which happens typically in the case of aromatics, you see aromatic comes downfield, down means downfield shifted. The hydrogen for the aromatic is also, we know, comes around 7 to 8. So, that is also downfield shifted. So, that means carbon and hydrogen chemical shifts in a CH moiety are correlated, they have a positive correlation. So, this is an interesting thing which was discovered sometime long time back, and in fact, there is a formula which we will show in this next slide, which says that if you know the hydrogen chemical shift from 1D NMR, you can approximately calculate the carbon chemical shifts of the CH system by using this formula. So, you just have to take the if you know the carbon chemical shifts, you multiply the carbon chemical shift with this, and then you get the hydrogen chemical shift of a given CH pair. Similarly, if you know the proton chemical shifts, you can multiply the proton chemical shift into this value and subtract 9.85, you get the carbon. For example, let us take a methyl system. In a methyl, let us say you have a chemical shift which is around 1 ppm. So, remember chemical shifts of methyl hydrogens, they come somewhere between 0 to 2 ppm. So, let us say we have a system where we get 1 ppm as a chemical shift of a methyl proton. I multiply 1 into 20.9 minus 9.85 will give me roughly 10. That means, this carbon of that methyl carbon will be 10 ppm roughly. Similarly, for hydrogen, let us say we take aromatic system. So, aromatic we know comes typically somewhere around 140 ppm. If you multiply this 140 with this and actually you do the math, it will come somewhere around 7 ppm. So, you see that hydrogen for aromatics we know comes somewhere around 7 ppm, and this is what is basically coming out of this, that was between 7 to 8, let us say 7.5 ppm. So, the carbon will be around 140 ppm. So, this is a very interesting correlation, an empirical correlation which was discovered, that whenever a proton chemical shift increases, the carbon chemical shift also increases, and this will be of some relevance when we come to 2D NMR, especially when we look at the heteronuclear NMR spectroscopy. Now, this slide here we are listing some of the websites where you can actually visit. It will be a good exercise for you if you can go to these websites. Some of them in fact have online where you can try out that you give a structure of the molecule and it will predict the chemical shift. So, these are basically softwares to predict proton and carbon NMR chemical shifts. When we say spectrum, basically it means we are trying to get the chemical shift values given the structural information. So, if you know the structure of the molecule, you feed the structure and to one of these softwares, and the software will then give you the chemical shift values, what you expect, and then that if you compare with your spectrum, you can now do what is called assignment, means given a chemical shift value, a peak in a spectrum, you want to find out to which carbon or proton it belongs to in the molecule. So, if you know the structure, you predict the chemical shifts of hydrogen and carbon and you match it with the chemical shifts you get from the NMR spectrum. So, that is called assignment, and many of these help you to do that. Some of them are freely available, some of them are paid, but overall you get a good idea from this. So, all the things which we worked out in the previous slides was basically are all implemented in these softwares. So, now let us continue with how we analyze the chemical shifts of carbon spectrum 1D NMR. So, what we are going to do is the first approach, that given a structure can I try to assign the peaks which I get in the 1D spectrum. So, remember what we did last time was that given a structure we try to predict using some rules, but now we are not going to predict the chemical shift values, rather what we will do is we will see the spectrum and try to figure out which peak in the spectrum corresponds to which carbon atom in this molecule. So, similar to what we did in hydrogen, that given a structure and the spectrum we want to now assign the particular carbon to a proton. So, again some recapitulating, we are basically doing three things in this proton and carbon NMR. First thing we are doing is that we are trying to predict the chemical shifts of proton or carbon using some rules which we saw, that is one thing. Second thing what we did was, given a spectrum and the structure again, we want to try to figure out that based on the J coupling, based on the chemical shift value roughly, what is the which peak will correspond to which proton or carbon. So, same thing we are going to do here. And the third thing which we did, which we will do here as well, is that we looked at, given only the molecular formula, we do not know the structure, and we are given the molecular formula and a spectrum, we have to now find the structure. Okay. So, right now what we will do is, given a spectrum, find the assignment. So, this is the spectrum shown here for this particular molecule. So, now our objective is that to figure out which proton, which carbon corresponds to which carbon here. So, first thing, if you notice in this molecule, let us try to look at the functional groups. So, here we have an ester functional group. So, remember for ester, if you remember the chart, or if you can go back to the chart, you will see that the ester carbonyls come somewhere between 160 to 175, and that is what we are seeing. We are seeing a peak around 170 ppm, which definitely has to now correspond to this carbonyl carbon. So, this carbon is coming from here. Then let us start from this corner. So, this is, you see, this is CH3, which is away from all the functional groups, I mean all the electronegative functional groups. So, that means this will have the most upfield shifted carbon, because the inductive effect is the lowest. So, therefore, you would expect that this carbon would now correspond to the most upfield shifted carbon peak, which is here. So, that is basically the carbonyl assignment which we just discussed, and this is the CH3, which is this peak. Now, come to this CH2. Now, this CH2 is closer coming to here, but this CH3 is also coming close to this. So, that means there are two peaks which are very close to each other, and that means one of them is corresponds to this CH2, this carbon, and another peak corresponds to this carbon. Why we are saying this? Because the idea is that as you go away from functional group, I mean the electronegative groups, your de-shielding effect reduces. So, that means this is more shielded with respect to this, but it is less shielded with respect to this, it is somewhere in the between, in middle. Similarly, this is also close to this. So, therefore, this and this will come very close to each other, and that is what is happening here. So, the smaller peak corresponds to this. Of course, the chemical shift difference is very small. So, obviously, it is not straightforward to find out whether this tall peak is corresponding to this carbon or this tall peak corresponds to this carbon. For that, we will have to go to 2D NMR, which we will see, that is where the 2D NMR helps us, but right now we will only look at 1D. So, now based on these, we can say that one of them is this carbon and the other one is this carbon. So, we will now tentatively, or we will assign that these two are coming from those two carbons. Typically what happens is methyls are very strong peaks in NMR. In proton also we get them very strong peak, similarly in carbon also we get very strong peaks. So, therefore, we use typically the tall peaks are usually associated with CH3. Now, coming to the remaining peak has to correspond to then this CH. Now, why is this coming so much at 60-70 ppm? That is again, remember, this is directly attached to oxygen. So, because of the electronegative effect, the shielding, it is directly influenced by this one bond carbon oxygen bond, and therefore, this CH2 comes very much downfield shifted and it comes at 65 to 70. This is also something which we saw in the proton in the beginning, that CO group comes somewhere between 60 to 70. Now, if I record a proton spectrum which is not shown here, we are not going to look at the hydrogen proton spectrum right now, but that proton also, remember, was coming around 4 to 5 ppm because of this oxygen electronegative. So, this is how we can assign for this particular example. Let us look at another example. This is also, remember, all these molecules we have been looking at from the proton angle. So, we saw the proton spectrum earlier a few classes ago, and there also we saw the same molecules. So, therefore, we are going to look at the same molecules again, but now we are analyzing the carbon spectrum rather than the proton spectrum. So, let us look at the spectrum of this molecule. So, what do you see? Now, let us look at how many types of carbon are there. So, if you see, there are only 2 types of carbon, or 3 types rather. I mean, this is a quaternary carbon. So, this is one carbon. Second is these two are symmetrical. So, they will be equivalent. So, they are having the same chemical shift. So, this is another carbon, second type, and the third type of carbon is this, because both of them again are equally symmetrical and they are chemically equivalent. So, there are 3 types of carbon. So, we expect 3 types of peaks, 3 peaks. Similar to what we saw in the proton, counting the number of peaks, a group of peaks in proton, a bunch. So, let us say we call the multiplet structure as one bunch, called looking at the one bunches of peaks, we saw that we can find out the number of types of hydrogens or protons. Similarly, here by counting the number of peaks, we can find out how many types of carbon are there, but we will see this rule does not always hold true, because sometimes some peaks are missing, sometimes the OH peaks are broad. Similarly, in carbon we will look at aromatic cases, there also it is sometimes not easy to count the number of peaks, but roughly you can actually estimate the number of carbons simply based on looking at the number of peaks. So, if I go back to the previous problem, there we had 1, 2, 3, 4, 5 types of carbons, and here also we have 1, 2, 3, 4 and 5 carbons. So, 5 carbons we got 5 peaks, 5 types of carbon and 5 peaks. Similarly, here we have 3 types of carbon, we expect 3 peaks. So, let us begin the assignment. How do we assign which peak is which carbon? Again we can use simple logic, that whenever you have an oxygen attached to a carbon, it comes somewhere around 50-60 ppm, but remember this is OCH3. So, therefore, the CH3 also comes somewhere between 0 to 20, but 0 to 20 is not, will not hold if there is an oxygen attached. So, again if you look at that chart which was we had seen earlier, it was somewhere between 50 to 100 ppm given for the OCH2 or CH3, and this is basically coming from there. And this lone carbon is attached to 2 oxygens. So, if you see this quaternary carbon is attached to 2 oxygens, and therefore, you expect double inductive effect, and therefore, it will be much more downfield shifted, this carbon compared to this carbon, because this is attached only to 1 oxygen. So, by that logic, this will become the quaternary, quaternary means C carbon, and this will be the OCH3, and then what remains, that is upfield shifted, that is a pure methyl, that is that coming at this standard value somewhere between 0 to 25 ppm, and this is what is shown. So, this is the exact assignment which we just discussed. One thing we can keep in mind from a practical point of view is, whenever you have a quaternary carbon, a lone carbon, it is always a little lower in intensity compared to other. And why is this so? The reason for that is that whenever you do not have any hydrogens attached to a carbon, it has a very long T1 relaxation. So, whenever you have something which is a long T1 relaxation, it is not completely recovered to its original magnetization when we apply a 1D pulse. So, this is something we saw earlier, that you need 3 to 5 times the relaxation time T1 for the relaxation delay value. So, if you have a long relaxation time, you need correspondingly longer relaxation delay. But we do not practically is possible to do that, because this may run into several tens of seconds. So, we cannot afford to wait for 5 times 10 seconds, which is about a minute, whereas this carbons may have a short relaxation time, they may have only a few seconds. So, idea is to quickly capture the chemical shifts without waiting too long, but if you do not wait sufficiently long, the intensity is reduced because of the incomplete relaxation, T1 relaxation. And that is why the peak intensity of this quaternary carbons usually are very weak. We will see also this in case of aromatic systems, aromatic quaternary carbons. So, let us move on to the next example here. So, this is the CHCO which is attached to this is an acid, carboxylic acid group, okay, and this is a secondary halogen. So, secondary carbon which is having a halide substitution. So, this is the molecule also we looked at when we analyzed the 1D proton spectrum. So, the same molecules has been taken up here. So, if you now let us see the spectrum of this molecule, here you can see now again there are 3 types of carbon. There is this methyl carbon 1, this is CHCl carbon 1C, and this oxygen is attached carbonyl carboxylate group at this C, and therefore, it is coming at this position. Now, again if you look at the chart of carbon expected peaks, the values, we saw that carboxylate comes somewhere around 180 ppm, and that is what is shown here, that there is a peak at 180 ppm, and that is little bit downfield compared to the ester group. So, if you recollect, there is a slight distinction between ester and acid. In case of ester, it comes somewhere around 160 to 170, whereas in the carboxylate acid, in a carboxylate group, the carbonyl, this carbon comes around somewhere between 170 or 80 to 190. So, this is the peak which corresponds to this carbon, and this side this is a methyl group, and because this carbon is attached to an electronegative carbonyl halogen. So, you expect this carbon to be de-shielded, and that is what is coming, it is coming quite de-shielded at around 50 ppm, whereas this CH3 which is a regular methyl group is away from this, and that will be therefore less de-shielded, and it comes at its regular position. So, again see, if you look at the intensities of these peaks, keep in mind the intensities of these peaks are no longer proportional to the number of carbons. For example, if I expect they are proportional, then I would have expected all of them equal in intensity. Why? Because they are say one carbon. So, this represents one carbon, this represents another carbon, this represents third carbon. So, there is 1:1:1. So, you expect one intensity, but equal intensities for all the 3, but that is not the case in carbon, because again the reasons were given as T1 relaxation, long T1 relaxation, and second is the NOE effect, because we decouple. So, look at these lines, they are sharp single peaks. Why? Because they are decoupled, the protons have been removed, I mean the J coupling has been removed from protons by decoupling, and that also affects their intensities. So, the intensity is no longer directly reflecting the number of carbons, unlike in the proton. In the proton case, this is not the situation, they are very quantitative. So, looking at now the assignments, this is what we discussed, the 3 carbons are very easy to assign. Basically, we are using logical arguments here. The logical arguments is electronegative effect, the carbonyl where you expect them, where you expect the methyl, and so on. If you want to get an exact match, you have to look at, you can calculate based on those rules we saw, and from there also you can see which is matching. So, we will look at an aromatic spin system, aromatic case, where aromatic system is shown here, and there is this carbonyl attached to this. So, this is a ketone. So, now we are looking at a ketone functional group. We have seen carboxylic acid, we have seen ester. Now, let us see how what happens in case of a ketone. So, ketone, the spectrum of this molecule is given here. So, let us try to assign, means match which carbon could be which. Again, by logically you can say that this carbon which is away from all these groups could be the most upfield shifted, because and that comes at its regular methyl. So, this is something what you can directly say, this coming from here. Similarly, this ketone group, again if you look at the chart we saw in the chart of chemical shifts, there you will see the ketone is the most downfield shifted carbon, it comes close to 220 ppm. So, that is what you see here, there is a very downfield shifted peak coming around 220 ppm, and that therefore has to come from this ketone C carbonyl group of the ketone. Now, if you look at this region somewhere between 120 to 140, that is where your aromatic spin system comes. So, typically what happens is when you are trying to simply assign this molecule to the spectrum, we do not look at the details of these peaks here in the aromatic region, because again like we saw in proton, you have a complication here called strong coupling and so on, and it may happen that there is lot of overlap and there is more of signal intensity loss, etc. So, what typically is done is by just qualitatively you just look at the region, and if you see peaks in this region, you can very well be assured that there is a aromatic spin system. So, this is how qualitatively you assign. Also, if you look at this peak which is a little isolated from this bunch and it is lower in intensity, that could be therefore that could be coming from the quaternary carbon, this carbon here, which is not attached to any proton like we saw in the previous case. So, therefore, this type of a signature, this type of a profile and this type of a spectrum is typically then assumed that there is an aromatic group here, and we do not go into detailed analysis of each and every peak, but this is we can say there is an aromatic moiety in our molecule, and that is basically this moiety. Now, the remaining aliphatic we can assign based on the isolated peaks. So, this CH3 we already saw is could be this, and this CH2 now is close to this. Similarly, this is close to this, both are equally from this, but if you see this CH2 is little bit downfield shifted more would be because it is attached to an aromatic group, which is an electron withdrawing group. So, that will also withdraw the electron density from this carbon, and similarly this carbonyl also will have. So, it has a double inductive effect. So, you can expect that this carbon will be slightly more downfield shifted compared to this carbon, and that is what you can see here. So, we will see the assignment, let us see the assignments. So, this carbonyl is this peak which we already saw, this methyl is this, and you can see here that because of the double electron withdrawing groups present on this carbon, it is little bit downfield shifted more compared to this carbon which is only attached to one CO which is electron withdrawing, whereas this carbon has two electron withdrawing groups close to each other directly bonded, therefore, you expect downfield shift. So, you see by this kind of a logic, typically you can assign the carbon chemical shifts, and we rarely record the coupled spectrum. Usually it is always the decoupled spectrum and therefore, it is just based on the qualitative aspects. Of course, if you have the multiplicity idea and so on, remember we saw that we do not get multiplicity from 1D carbon. For that you have to do a special experiment separately to get that information, and that experiment if you do, then you can further see whether it is a methyl carbon or a methylene carbon or a methine carbon. For example, in aromatics they are all CH. So, that kind of information comes from a separate experiment, not from this 1D, and that is also usually done. So, we will take that up later when we actually go for a full structure determination example in the later classes. So, let us now look at continue with this. So, this is aromatic group. This is what I was saying, that if you have a bunch of peaks at this region 125 to 135 or 120 to 140, we can very confidently be sure that there is an aromatic group present in the molecule. So, now let us look at the last aspect where we look at given a molecular formula. Again this is an example which we have already seen in hydrogen proton spectrum analysis. Now we are going to add information on top of that. So, we already had the proton spectrum and based on that we are analyzed. Now, what I am going to do is only add one more spectrum to this example and see whether our structure what we got is it conformed based on the carbon spectrum. So, if you look at this case immediately, so this from here this is the structure, this is the molecule. So, if I had only the proton spectrum with me, I would have not been sure whether what kind of CO moiety is here. It could be an alcohol. If there is an alcohol, it is OH, okay. But if there is a carbonyl, it is CO. So, that information is not coming from here. Of course, it can come from IR spectrum, but suppose I do not have an IR spectrum, I have only NMR. By looking at the spectrum, immediately I can see here that there is a peak at 220 ppm, and the 220 ppm is very strongly going to come from ketone group according to that picture chart which we saw. So, therefore, immediately I can conclude that there is a ketone functional group in this molecule. That means, there is a C double bond O. Now, I have remaining 4 carbons to look at and the remaining 10 hydrogens. So, there could be now the aliphatic system. So, again remember this is repeat of what we saw, that if you have a septet means 7 peaks, most likely it is an isopropyl group CH3 CH CH3. So, that could be the CH3 CH CH3 attached to a carbonyl group, and there could be isolated methyl because there is no J coupling. So, that means there are 3 types of protons and 3 types of carbon in the aliphatic. Of course, this is a 4th type of carbon, but that is ketone. So, this is basically fairly straightforward. We already analyzed from the proton side, or carbon is only helping us to confirm. So, this is the structure of the molecule which we saw earlier, and this is explaining the carbon spectrum, because the carbonyl is a ketone which comes very downfield shifted, and because of this CH3 is an isolated, it will be coming from here, and the one which is attached to CO, this CH is slightly downfield shifted, which will come from here. But again, which carbon is which carbon, we are not sure from here. That connection between this proton spectrum and which carbon, that is part of the 2D experiment. We will do that later. So, right now we are looking at isolation, means I am looking at this spectrum in isolation with this spectrum, means separately, but a combination of these two would also give me the information as to which carbon, which peak here matches which carbon proton here. Okay. So, that information is not in this, because we are looking at separate 1D. So, let us come back to this particular case. Now, if you see here, again there is a single oxygen, but again I do not know whether there is a ketone functional group or there is a alcohol OH and so on. So, how do I find that out? Again, if you look at the carbon spectrum, you see there is no peak here in carbonyl region. So, that means there is no carbonyl group here, there is no ester. Ester, of course, there is no 2 oxygens, there is only 1 oxygen. So, there is no carbonyl peak in this region. So, it has to be a alcohol OH. Now, if you look at the bunch of peaks here between 7 to 8, similarly a bunch of peaks here, remember this all corresponds to aromatic groups. So, therefore, there is an aromatic moiety in this molecule. There is an aromatic moiety, there is an OH group. Now, if there is an OH group, you expect a downfield shift for the hydrogen which is near to the OH, that is CHOH. Similarly, here also that this peak which is between 60 to 70 is again CHO kind of a molecule, moiety in the molecule, and this quartet and triplet could be a ethyl group CH3 CH2. So, the CH3 will get so CH2 will be a quartet and CH3 will be a triplet. So, let us see this molecule. This is what is shown here, this is aromatic system, and this is this particular molecule. So, you can see that there is an OH group. So, this CH2 corresponds to this is a triplet, and this CH2 which is in the middle is actually a quintet. So, this is not a methyl, this is a CH2 which is a quintet. And why is it a quintet? Because there are 2 hydrogens this side, 2 hydrogens this side. So, 2 plus 2 4 plus 1 makes it 5. So, this is in the middle. Now, if you look at this peak here, this carbon and hydrogen, this is attached to an electron withdrawing group, the benzene, the aromatic ring. Therefore, they expect to be downfield shifted. So, out of these 2 peaks here, the methylene, one of them is this carbon, other is this. But what about the protons? The protons, this one which is here will be more downfield shifted relative to this, because of the electron withdrawing group of this, okay, and that is this peak here, because it is coming in at 3 ppm, it is downfield shifted, and there are triplet here because this 2 is coupled to 2 protons here. So, according to the n plus 1 rule, these 2 protons will be equivalent, I mean they will have triplet multiplet from J coupling, and this hydrogen, this proton is downfield shifted because of the OH that is coming from here. And now, coming to carbon side, this 60 ppm which is downfield shifted is this carbon, and between the 2 carbons the upfield shifted will be this one, because it is less shielded, it is away from the de-shielding effects, it is in the middle, whereas this is close to this group. So, therefore, this carbon here will be this carbon. Okay. So, this is how we assign the carbon spectrum. So, we have looked at some of the examples how we can assign carbon spectrum based either on the structure directly or in combination with protons spectrum. or we can actually predict the carbon chemical shifts directly based on the structure, the rules which we have seen, some of the rules. So, we will now complete this part of the course here, that is looking, we have looked at 1D NMR of proton and carbon and their interpretation in different ways, how what factors affect the chemical shifts, how to analyze 1D NMR and so on. So, this completes the second part of the course. The next part of the course now will begin with 2D NMR, where we will now look at 2D NMR chemical shift correlations between proton and carbon, and we will see how they are recorded, what are the practical aspects and how do we actually analyze them.